right, so with section 8.3, we're looking at relative rates of growth. This is one of the things that we've looked at in ways with all of the things we've done. When we looked at limits, when we compared limits, it rears its ugly head in L'Hopital's rule when we end up with 0 over 0 or infinity over infinity, and we can't just make a decision and say that's 1 because we don't know which one's going faster to 0 or to infinity, the top or the bottom. And we're going to see this now a little bit anyway, hopefully, that relative rates of growth are very important to determine what function's growing faster. Now, the function y equals e to the x grows very fast. We know it from its graph. If we could graph it on a chalkboard, and we end up with one that looks like this. So if x is 3 inches, y is about 20 inches. So 3 inches over, and we've already grown 20 inches vertically. When we get to 10 inches on the x-coordinate, y is 1/3 of a mile. And at 44 inches, y is 2 million light years vertically. So when we talk about growing fast, we're literally talking about growing very, very, very fast. Now, we've gone less than halfway across the board horizontally, and already the y value would reach the Andromeda Galaxy. At 64 inches, the y value would be at the edge of the known universe, 13 billion light years. Now, the function y equals natural log of x, of course, which is the inverse of e to the x, grows very slowly. If we graph it on the chalkboard, it looks like this. So we would have to move 2.6 miles to the right before the line moves a foot above the x-axis. And if we go out in the x direction, 13 billion light years to the edge of the universe, the chalk line will only have reached 64 inches tall. So the function y equals the natural log of x increases everywhere. But it does increase very, very slowly. So the slope is always going to be positive, but it's going to be very, very tiny slope, positive slope, as you get further and further out. So now the definitions: faster, slower, same rate growth as x approaches infinity. Let f of x and g of x be positive for x sufficiently large. F of x will grow faster than g, and g grows slower than f as x approaches infinity if we take the limit as x approaches infinity of f of x over g of x, and it equals infinity. Now this is the limit of one function divided by the other function, and x is going to infinity, and if that limit goes to infinity, then the top function grows faster. If we flip that over, and g of x over f of x limit as x goes to infinity goes to 0, that means that g of x grows slower than f of x, or f of x grows faster than g of x. So this is actually pretty straightforward, depending on which one grows faster, whether you're going to infinity or 0. If you go to 0, the one on bottom is growing faster, and if you go to infinity, the one on top is growing faster. Now, f and g will grow at the same rate as x approaches infinity if the limit as x approaches infinity of f of x over g of x equals some limit, some constant that is not equal to 0. So with this situation, L can be any number other than 0 as long as that limit approaches a constant. Now it can't go off to infinity. Infinity is not really a number. But if it goes to 10 or 100 or even a million, even if the limit is a million, they're growing at the same rate. Warning, please temporarily suspend your common sense. Most of you guys do that all the time. Some of you don't even have any to suspend. According to this definition, y equals 2 to the x does not grow faster than y equals x. By definition, defining this way, it doesn't. Because if you did the limit, you're going to get 2. Now looking at this, we do know that it increases faster, but it's not growing faster. That's the thing. The book says that that f grows faster than g means that for large x values, g is negligible when compared to f. In these cases, they're growing, one's just double the other, so they're going at pretty much constant rate. Grows faster is not the same as has a steeper slope. So kind of get that out of your mind. So which grows faster, e to the x or x squared? Well, if we take the limit as x approaches infinity of e to the x over x squared, we're going to get infinity over infinity. So of course that's a L'Hopital's problem. When we take the L'Hopital's rule, when we use L'Hopital's rule, then we're going to get e to the x over 2x. And then we try again, and guess what? It's still going to be infinity over infinity. So we use L'Hopital's rule again, and we're going to end up with e to the x over 2, which is going to go off to infinity as x approaches infinity. Therefore, what do we know? We know e to the x grows faster than x squared. Now, we can, of course, confirm this graphically by, well, looking at the graph. And if we do this, e to the x over x squared, we graph that. Notice what happens when we get out this direction. It's going up, and then going to infinity, it's not actually going to approach a certain value. So e to the x is going to take control of this value and go off to infinity. Now, growing at the same rate is transitive. In other words, if two functions grow at the same rate as a third function, then the first two functions grow at the same rate. So A equals C and B equals C, then A equals B. That's what we're talking about. If A equals C and B equals C, then A equals B. So if two functions grow at the same rate as a third function, then the first two functions grow at the same rate. All right, so example, show that f of x equals the square root of x squared plus 5 and g of x, 2 square roots of x minus 1 quantity squared, grow at the same rate as x approaches infinity. So let's let h of x equal x, because we're going to prove that each of these grow at the same rate of x. Now, Hopefully you can kind of see that. Square root of x squared, remember, as we go off to infinity, what's going to happen to the 5? It's going to be negligible. So we can think about this as the square root of x squared, which is just going to be x. So these should grow at the same rate. We're going to prove it though. Same thing here. If we have 2 square roots of x minus 1 and we're going to square this thing, well, then as x goes off to infinity, that negative 1 is going to be negligible even though it's squared, and we're going to end up with square root of x squared. It's going to be similar to x. The 2 doesn't really have a thing to do with it. So that's what we're trying to prove. We're trying to prove that both of these, since the limit of this thing over that thing is not going to be an easy limit, we're going to prove this to grow at the same rate as that, and this to grow at the same rate as that, and then by the transitive property they have to grow at the same rate. So that's why we're using h of x equals x. So the limit as x approaches infinity of the square root of x squared plus 5 over x, and as x goes off to infinity, we can rephrase this as the square root of x squared, and we're going to be able to put all that in one radical and divide the x squared into both parts. So we end up with 1 plus 5 over x squared. As x goes to infinity, what's going to happen? Well, we're going to end up with 1 plus 0. So we end up with 1. Well, what does that mean? That means that the square root of x squared plus 5 and x grow at the same rate. Remember, if we do that test, we end up with a constant other than 0, then they grow at the same rate. All right, let's do the same thing with x and the 2 square roots of x minus 1 squared. So the limit as x approaches infinity of 2 square roots of x minus 1 quantity squared over x, when we plug that in, we first want to get this thing to look similar to one another, and we can do the same thing similar to what we did right here, where we did the square root of x squared. We can do the square root of x quantity squared. That's still x, right? But now we've got something that we can actually deal with, because we've got both of these squared, so we can put the whole thing in one big set of parentheses and divide that into both parts. So the 2 square roots of x over the square root of x, those are going to cancel out, of course, and 1 over the square root of x is going to go to 0. So those cancel out, leaving me with 2 minus 0. Oh, sorry, 4 because it's squared. That's right. Forgot the little squared thing there. So this limit, being 4, verifies by the transitive, or by the test, that these two things grow at the same rate. Therefore, by the transitive property of growth, we know that if the square root of x squared plus 5 grows at the same rate of x as x, and 2 square roots of x minus 1 quantity squared grows as the same rate as x, then those two grow at the same rate. And here you can also see they actually put in, here we're doing f over h, here we're doing h over g. You could flip that over. That's where the 1/4 comes in, by the way. And that limit would be 1 times 1/4, which is 1/4. Therefore, they grow at the same rate. That's the transitive property in a nutshell. All right, and that is all of 8.3.